LVDT stands for linear variable differential transform. Linear variable differential transform. Many times in examination I used to see the expansion itself is written wrongly by the students. So learn the expansion first. Linear variable differential transform. This is used for measuring linear displacements. Of course, there is something called RVDT, rotational variable differential transformer, or rotary variable differential transformer. They are used for measuring angular displacements. This is for linear displacement. This works in the principle of mutual induction. Induction means actually you have a current carrying conductor. You take not a current carrying conductor. Current carrying conductor also we can explain in mutual induction, but the simplest way to explain is you simply take a coil. Coil means what? Copper wire. Not with plastic insulation, only copper wire. What you see normally inside the motor and all, the coil is wound in the big motors like that, copper wire, probably with an insulation coating. Bind it in the form of a coil like I have shown here, and simply connected to a multimeter, a sensitive multimeter, or a galvanometer. Galvanometer is actually a sensitive multimeter and sensitive voltmeter. So if you connect that, simply a wire, take a normal permanent magnet, just move it on top of it, very close to it. You need not touch, just without touching. In the magnetic flux region, you simply move. When you cut the magnetic lines here, you see an EMF is induced in the coil, and you see a current is flowing inside the conductor. Normal conductor, nothing else. Simply a wire, you produce electricity. That's how electricity is produced. The generator principle is like that. You have a magnetic flux, you cut, you generate EMF, electromotive force, EMF. And of course, because of EMF, there will be a current, and that current you will be able to see in the galvanometer. Okay. So this is induction principle. This is induction principle. One permanent magnet and one coil. What is mutual induction? When you have a current carrying conductor, around that coil, there will be a field. Okay? There will be a field, and that field, if it is cut, again this the EMF is induced from one coil which is carrying current, from another coil which does not carry current. You will be able to induce EMF from one coil to another coil. Normal induction is one permanent magnet, one coil. Mutual induction is I have a coil. When current is flowing through that, electromagnetic force will be there around that coil. To suppress that electromagnetic force, normally we insulate the wire with plastic coating on top. A thick layer of plastic will be there, so that those effects are less. Normally, other measurements and other things are not affected by that. So any current carrying conductor will have a flux around it. If you disturb that flux, again you can induce EMF in the disturbing coil. So you have, instead of this permanent magnet, you remove this permanent magnet, you have another coil which is carrying current, and then move on close to that, close proximity to that coil, you move this empty coil which is connected to no current, nothing is connected. You have only a multimeter or a galvanometer. You simply connect, you move on top of it, you see EMF is induced and a current is flowing in this circuit. This principle is called mutual induction. Self-induction and mutual induction. Okay, this is mutual induction. Actually, this was accidentally found by one scientist. He is not a scientist initially. He was an attendant working in a big scientific laboratory. So when he was an attendant, there used to be big projections. Today we have data projectors. In those days there is no data projectors. They will have optical projectors. We have a light and bulb, and there will be a film for keeping the handwritten films. Whatever is written or drawn on that film will be projected big so that people will be able to read it better or whatever. They are all optical projectors. So something was kept on the some galvanometer or something like that was kept on the that optical projector. The attender who is working in that particular lab took some permanent magnet very close to that. Let's say he is carrying that. He carries the permanent magnet very close to that. He was alone in the lab and it was dark. The projector was on. The optical projector was on. He found something is shaking. Initially he got scared. Because nobody is there, nothing is disturbed, and galvanometer is suddenly showing some reading. So some ghost or something, got afraid. But later he repeated this, same thing happened, and other times it is not happening. So first he confirmed it is not because of ghost, there is some scientific principle behind it. Later, along with other fellow scientists, he found out that it is because of mutual reflection that EMF is induced and galvanometer is showing kind of reading through it. Okay. So it was actually found by the people accidentally. Okay. So mutual induction is inducing EMF from another coil, which is having current flowing through. Okay. So, do you know what is meant by transformer principle? Transformer works on mutual induction. Transformer. How many of you don't know the working principle of transformer? If you are not raising the hand, I will randomly ask you to explain what is transformer principle. How many of you don't know transformer principle? Oh, all of you know. Very good. Sai, can you explain what is transformer principle? You have to open your mouth and talk, then only I can hear. I know you are reciting in your mind, but somehow I have inability to hear your mind voice. Then you should raise your hand. How many of you don't know transformer principle? Working principle of a transformer. What do you think?
Primary coil indicates another EMF in secondary coil.
In secondary coil.
And it steps down.
Yeah, there are step up and step down transformers. So it uses what principle? Induction principle, right? Mutual induction. Okay. Your LVDT also will look like a transformer. You have something called primary winding, you have something called secondary winding. Primary winding, you will have a current carrying conductor, so there will be a magnetic flux around the coil. Whenever a metallic core that disturbs this magnetic flux, an EMF will be induced on the secondary winding. Fine. Only difference between the transformer principle and LVDT working principle is, in transformer we will have one primary winding and one secondary winding. One primary winding and one secondary winding. In LVDT we will have one primary winding and two secondary windings. See, this is primary winding. This is one secondary winding. This is another secondary. So transformer principle means you forget about one secondary winding, or you consider continuous coil. There is no break here, there is no this line. You continuously, like this, you have one in the bottom. That is transformer principle. Okay. There is a formula, the number of turns and the thickness of the wire, all that affect the winding. N1 by N2 equal to E2 by E1 equal to I1 by I2. So at the cost of current, voltage will be amplified, or at the cost of voltage, current will be amplified. Depending upon that, whether you are amplifying the voltage or reducing the voltage, you call it as step-up transformer or step-down transformer. They are all transformer principle. Okay. The working principle is same. Primary winding will have the supplied by us around that coil. If there is a current carrying character around that coil, magnetic flux will be set. Any metallic part, the magnetic part disturbs that. Not magnetic. It can be simply a metallic part. It need not be a magnet. So it disturbs that magnetic line, and EMF will be induced on the disturbing part. Okay. Suppose you take a simply copper wire, make it in the form of a coil, and simply move in the magnetic field. You need not touch the primary winding. Without touching the primary winding, if you disturb the flux, magnetic flux, the current will be induced in the secondary winding. There is no connection at all, no wire-to-wire connection, but still you get electricity, okay, on the secondary winding. This principle is called mutual induction. Transformer works in this principle. Okay, fine. Same principle we will use in the LVDT. That is why it is called a transformer. The working principle is same as transformer. That is why we use transformer. I also told what is the difference between a transformer and LVDT. In transformer we use only one secondary winding. In LVDT we will use two secondary windings. And not just two simply we use. We have secondary winding 1, we have secondary winding 2, and the difference between these two we take it as output. Okay. Secondary winding 1 will give one voltage output. Secondary winding 2 will give some voltage output. Let us say this is V1, this is V2. V1 minus V2 we will take it as output. Since we take differential output as the output, it is called differential transform. It is called differential transform. What is meant by linear variable? The object which is disturbing the magnetic flux moves or varies linearly. If the object which is disturbing the flux is actually moving linearly, the linear movement, not rotary movement in that sense. It is not linear and non-linear. It is linear, linearly it moves. Proportional to or linearly proportional to that movement, your voltage varies. There are two reasoning we will give. Okay, one is this linear has two meanings. Both are correct. One, it is not rotary movement; it is a linear movement. You know what is in the linear movement? A straight line movement. In that sense, it is linear. A non-linear, non-linear means what? The curve is linearly proportional. The curve is non-linearly proportional. In that sense also, it is linear. In both the sense, here we have linear variable. What is that? This is the push rod, this is the core. This core moves in the linear fashion, not in the rotary motion. It is a linear motion that causes the flux damage, cutting of flux lines. Because of that, the EMF is produced. So you call linear variable differential transform. That is one name reasoning. Another name reasoning, proportional to the core movement. You move 1 mm, there is a small voltage. You move 5 mm, proportional to that there is 5 times of that voltage. Proportional to the linear core movement, you get the voltage output. In that sense also, people call this as linear variable differential transform. Proportional to the core movement, you get the voltage output. So in both sense, it is linear variable differential transform. That's how the name was derived. Okay. Up to this is clear, all of you. So it works on mutual induction, transformer principle, two secondary windings, differential outputs are taken, so it is differential transformer, and the linear motion is converted into the corresponding differential voltage, so it's called linear variable differential. RVDT means rotary variable differential transformer. It is not the linear motion there, it is rotary motion. The object which is cutting the magnetic lines will move in an angular fashion. Move in the angular fashion. So it is rotary variable differential transformer. Okay. That is RVDT. For LVDT, the construction of items. You have a shell, primary windings, not primary windings, primary winding because there is only one primary winding. Secondary windings, here it is actually supposed to be plural. You have core, power supply, and display. These are all the major items in it. Power supply, how much voltage, how much current, what is the frequency, all that matters. Okay. Normally, the frequency is what is that matters a lot. You see, 5 kilohertz to 20 kilohertz AC excitation is applied to primary wire. 5 kilohertz to 50 kilohertz. In the Tamil Nadu electricity board or Kerala electricity board or whatever electricity board you receive from your home, what is the frequency of voltage or current that you are getting? 50 hertz. Okay. In some other country it is 60 hertz. Normally either 50 hertz or 60 hertz is there. So we cannot use that as the excitation for LVDT. This is the specific range of the frequency range of interest for LVDT is 5 kilohertz to 20 kilohertz. That is the frequency range in which the inductance effect is dominating. Inductance effect is dominating, very high. Okay. Very low frequency range, the resistance effect will be more, and the very high range, capacitance effect will be dominating. And in that 5 kilohertz to 20 kilohertz range, people have researched and found the inductance effect is dominating. So you get better output in that frequency. It does not mean if you use lower frequency, the LVDT principle will not work. LVDT principle will work, but the output you will get perfectly when you use 5 hertz to 20 hertz. So that's the operating range. Of course, voltage you can have any voltage, 5 volt, 9 volt, 12 volt, any standard voltage. And of course, the rod, the core, push rod is simply an extension rod. It can be mild steel, aluminum, anything that you want, depending upon the load that you want to apply. And the core is actually a magnetic core. It's normally an iron core, which has the capacity to become magnet, but it is only used to disturb the magnetic flux developed by the primary wave. Okay? So we have shell. Shell is nothing but when you anybody has used LVDT in your lab, there is an outer casing in stainless steel. Everything is inside there. Everything is inside there. That covering object is called shell. So you will have a core. The cut section of that, this is both primary and secondary winding together, and you will have a box encompassing all this. That is a push rod. This can move left and right. This is winding, both primary and secondary together, let's say. And over top of it, you have a cover that's function. That is normally made up of stainless steel or any material that you want. Normally it is stainless steel. So that's about shell. Primary winding and secondary winding will have basically it is all copper wire windings, and depending upon the specification, the range, the voltage, all that, there is an electrical calculation similar to the transformer calculation. There in transformer our principle is either to step up or step down or at least ground isolation. These are all the reasons why we go for transformer. Here our purpose is we need to develop a primary winding, a magnetic flux, and secondary windings. There is no step up, step down, ground isolation is the purpose. We simply have to generate the magnetic flux that should be cut by the object of measurement, and secondary voltages need to be produced. So normally the secondary winding and the primary winding will have no step up, step down activities. Simply same number of turns, so that same voltage is trying to you are trying to use. About power supply, we talked about display unit. You will have a voltage output coming out of LVDT, which is a differential output. Differential output means V1 minus V2. V1 is the voltage output we get from secondary output 1. V2 is from voltage output 2. The differential output of these two will get it as output. That you connect it to the voltmeter with 7-segment display or LCD cell display, so that you will be able to read the display. Of course, there is a bit of signal processing that goes in between. It's not as simple as that we discussed, but at BTech level you learn this much. That's good. So you have the excitation signal here. excitation signal here. That's the first sine wave, and the output signal is shown here. I have shown both sine waves because it's a AC signal, alternating current signal. So you will have the sinusoidal representation. I have given both the amplitude in the same size. It need not be. It should not be all the time. So when the core is perfectly linking both primary and secondary. Let us say here also 5 volts is induced. Here also 5 volts is 5 volt voltage is induced. EMF is induced. Here also 5. Here also 5. What is the difference between that? 0. That will be the starting position of measurement for LVDT. Now you move the core either to left or to right. It has capacity to measure both in the positive direction and negative direction. Let's move towards left. When the push rod is moved towards left, the core also moves along with it. Now the core is ending here. So here the entire magnetic flux is covered by the secondary coil, and that is cut by this core. So 5 volts voltage is induced here, whereas here some portion is not linked by primary and secondary. Let's say only 4 volts are induced there. So now here it is 5, here it is 4. 5 minus 4, 1 volt will come as the output, proportional to this core movement. If you move further left hand side, it will be 2 volts difference, 2.1, 2.2, like whatever. Not like 1 volt after that 2 volt. Anything in between 1 and 2 also, the fraction values also will come. So as it moves towards left, proportional to this movement, left side movement, the difference in voltage will keep on linearly increasing, and that voltage you calibrate it and put it in terms of displacement. So much voltage means so much amount. So you will be able to read directly from the. Okay. That you won't get it as a DC value. Voltage difference is 1 volt means 1 volt. That you will get it as a the amplitude of this sine wave. Okay, 1 volt means it will be a small sine wave. It will be a small sine wave. 1 volt means, so this amplitude will be 1 volt. 2 volts means same sine wave, but now the amplitude is 2 volts. 3 volts means it will be like this. 4 volts, 5 volts. So this amplitude keep on increasing proportional to the core. Okay. Now, suppose if the core moves towards right hand side, in the middle position, this side 5 volt, this side 5 volt, the effective voltage is 0. When core moves towards right hand side, this side 4 volts, this side 5 volt, 4 minus 5 is minus 1 volt, minus 2 volt, minus 3 volt, things will come. Accordingly, here the shape will change. This will be minus 1 volt, this will be minus 2 volts, minus 3, minus 4, minus 5. So depending upon the movement, you will be able to get the voltage there. It will be a sine wave. By measuring the amplitude, you will be able to calibrate it to the. What is the block diagram installation of that? You have core displacement that causes change in the inductance. Okay, that changes the voltage that's being developed in the LVDT, and voltage is calibrated to give you the actual displacement upon calibration. That's the block diagram installation of LVDT. And what is the signal conditioning? Of course, it's a little more involved. I have removed these slides so that you will not find it difficult to follow. Preliminary explanation only we have given for LVDT. The lot of signal processing goes in between conversion of the displacement to the corresponding voltage. It's not straightforward as I explained. A lot of signal processing, oscillation, modulation, demodulation, all that happens. There is an oscillator which gives a high frequency signal that takes the signal core movement, signal proportional to the core movement gets modulated to the voltage signal. Then there is a demodulation circuit. Demodulation circuit removes the carrier frequency and takes only the signal. Then the RMS value or peak value, whatever that is measured from the signal, and then you get the visible. So there is a bit of signal processing involved. Typing I leave it. People who are interested, you come. We will explain to them in detail. So good amount of signal processing should be done to tap only the voltage difference between two secondary wires. If you go to the market, you want to buy, these are all typical specification I have given. We have explained the characteristics of instruments in detail. Using them, try to reason it out. In examination, you will be given some specification. You will be asked to comment on the specification. So, unless you know the specifications well, characteristics of instruments well, you will not be able to write anything there, or you will write something in general which will not be a correct answer. So study carefully, try to apply to this kind of specification, so you will be able to answer that. Linear range. What is meant by linear range in LVDT? The core is in the middle position. Here also 5 volts, here also 5 volts we explained. That time the effective voltage of the LVDT is 0 volts. As the core moves towards right hand side, the voltage difference comes and there is a proportional voltage. Okay. Up to certain distance, you see here 5 volts, here 4 volts. Effective voltage is 1. Here 5 volts, here 3 volts. Effective voltage is 2. As the core displacement, x-axis, voltage developed on y-axis goes on increasing. It has reached the tip of first winding. The first winding is almost done. Now the core does not link primary and secondary at all, but further core is moving. What will happen? Here it has reached 0 volts because there is no linkage. There is no flux linkage between primary and secondary by the core. Here there is no voltage developed, 0, but it starts further moving. Earlier here it was 5, as core moves, here it is 4, then here it is 3, here it is 2, here it is 1, here it is 0. So here it has already reached 0, cannot go beyond 0, 0 only in the one secondary coil. Another secondary coil, it was 5 volts, then that itself become 4, that itself become 3, that itself become 2. So you will see that as it goes linearly up to here, beyond which it starts reducing. Okay? At this position, here only one secondary coil is fully connected, other secondary coil is not at all connected by the core. That is the maximum linear range you can have. Beyond which, when you further move the core, you will see that here itself it is 5 volt. After some movement it becomes 4.5, 4, 3, 3.5, sorry 3.5, 3, 2.5, 2, 1, 0. It will start coming down. And finally you take out the core, 0 volts. This side also 0, that side also 0, so for us, the useful measurement range is only up to this. What is that? The core can be moved up to some flux linkage in the one secondary, full flux linkage in the other secondary. Up to that you can move the core. You cannot keep on moving the core. Okay, so core displacement has a direct relationship with the linear measurement. If you want attendance, I will give attendance. This is linear range of LVDT. Where and all can be used, some of the application case studies. LVDT is used in measuring the extension of the workpiece in tensile testing machine. Tensile testing machine. In tensile testing machine, what is that we want to do? We want to know what is the extension of this workpiece upon certain load. Strength of materials lab you people are doing?
Yes, sir.
Or already done?
Doing.
Doing. Okay. That at least you might have seen the demo. There will be a lot of other instruments are used. It's not the LVDT is only used for measuring extension of the tensile testing machine. It also can be used. So you have a test specimen of standard specification. Some load is applied, extension is happening. While extension is how much extension is happening for a given load we want to measure. So what do we measure? One side of here, what is the actual extension will take place. So one end you connect one piece. This is the core. Other end you connect the body. Body that means the shell. That you connect it to the other end. When extension happens between these two rods, you find that the core is moving to that extent, and you get the voltage output corresponding to that. One way of measuring. Don't know. Sometimes the workpiece is given the load till it breaks, and then it comes off. Product. You might have seen that. Whereas this LVDT can have only 10 mm range, plus 10 mm, minus 10 mm, plus 15 mm. The range of LVDT is very less. You cannot have plus 1 meter, minus 1 meter LVDT. I have not seen so far. Probably in the museums they may have the giant LVDT. But normally in the industrial purpose, plus or minus 10 mm, plus or minus maybe 50 mm maximum, not more than that. Typical LVDTs of that range. Whereas here, the gap maybe between two jaws of the tensor testing machine is more than 50 mm, so it's not favorable. So they have modified it like this. You have a wedge like this. You keep LVDT here. As the loading takes place, the extension takes place. This is fixed at end. Because of loading, this goes down. As it moves down, it slides down the wedge. As it slides down the wedge, the LVDT plunger, it is facing like this. As it slides down, the rod, which is spring loaded, will try to move out. This is spring loaded. This plunger is the push rod, is spring loaded. You leave it, it comes to the full extension. Okay. So you buy spring loaded plunger, keep it against the wedge. Because of loading, as extension takes place in the workpiece, the bottom portion of it moves down. LVDT also along with that moves down. As the unit moves down, the plunger is allowed to move out. The plunger is allowed to move out. Plunger means there is a push rod. Push rod moves out. Corresponding to this distance, you will be able to measure what is the extension that has taken place. We know what is the slope of this. We know what for this much of plunger movement, this much mm extension has taken place. There is a one-to-one correlation, so you will be able to correlate what is the extension in the LVDT. This is for leather industries, for cloth industries. All this, people find thickness of the leather using LVDT. You have two rollers. When thickness is, let's say, prescribed limit, it will have certain value. When thickness increases, this is a fixed roller. This roller can move up and down. So, depending upon the thickness, this roller will move up. If thickness comes down, it will come down. That movement is transmitted to the LVDT plunger, that's push rod, and that upward downward movement you will be able to use to measure the thickness of the units. Also, measurement of pressure in proving rate that we will be discussing in the next class. Measurement of pressure in the diaphragm gauge. When pressure is applied, you have a ring. When pressure is applied, the circular ring will become oval shape. Okay, and the both jaws will come down. How much that comes down is a measure of force or pressure here. Here, the pressure is applied to a diaphragm. Diaphragm means a membrane, a thin membrane, not thick, thin membrane. When pressure is applied, like a balloon, the membrane will become bulged, like a belly, it will become bulging. How much? Now it is straight, it's a six-pack condition now. When it is bulging, the belly condition, when pressure is applied. How much it comes out is a measure of the amount of pressure here. Upon calibration, you can directly read the pressure. There, LVDT is used as a secondary transducer, both in proving ring or in such application. Secondary transducer to measure pressure or force. It is also used for inspection of dimensions. For example, you have a bearing. Okay, you want to know the circularity of that, whether it is ovalic or whether it is perfectly circular. You take the bearing, fix it onto the jig, put the LVDT like this, rotate the bearing. If the radius is perfectly same, the LVDT will not move at all, it will be stationary. If it is oval, whenever there is a oval or eccentric comes, it tries to push the LVDT up or it comes down, so that any outing from the radius distance is a measure of oval. So you can check whether a circular object is circular and things like circular measurements. Typical example also will include the automobile wheel rim measurements. Lot of shapes will be there. At every place you want to check whether it is perfectly circular. So you put multiple LVDTs. Simply rotate once the wheel. In one complete revolution, if you get perfect circle, and that means there is not circle. The LVDT should not move at all. If LVDT is stationary, does not give any reading at all, that means the object is perfectly circular. If LVDT gives some reading other than 0, that means the circularity is not good, so you have to check and correct. It is also used for counting the currencies. Sheet means you go to paper manufacturing industries. 500 numbers you have to count and put it in one rim, one package. So manually, if you count, probably only 100 packets you will be able to put, and a lot of mistakes will be there. People use counters. There LVDT. RVDT, you have a core not in the linear form but in this form. The core is basically the one which connects the magnetic flux between primary winding and secondary winding. So here you have a core which connects the primary and secondary winding. This winding connection is because of the rotation of the shaft. The core does not move axially. It is rotated like this. Like a key, you put a key and rotate clockwise and anti-clockwise rotation. So that is why it is called rotational variable differential transformer. Other than that, the idea remains same for RVDT. Very rarely RVDT is used, but LVDT is very widely used in many industries. Advantages of LVDT: you have infinite resolution. In potentiometers, we had resolution problem, especially normal potentiometer, wire-bound potentiometers. We had a resolution problem. It jumps from one wire to the other wire, and resolution is dictated by the amount of turn that it goes, diameter of the mandrel. But here, there is no resolution problem, infinite resolution. Any small amount of motion, you will be able to measure using LVDT. High repeatability, good accuracy, wear and tear are almost nil. Because there is a moving part, there will be some wear and tear, but it is not as high as a potentiometer, where it has to make for a direct contact on the resistive material. And here, primary winding and secondary winding does not touch each other. Okay, the windings are not touching. Only at the end, there is a push rod that is moving. Of course, here there will be a ring, here there will be a ring, and only in the ring it will be touching. So that will be small wear and tear, but that is almost nil compared to other potentiometer. Also, electromechanical conversion is near ideal. Normally, the displacement is converted into electric signal. A mechanical energy is converted into an electrical energy. Isn't it? That conversion is almost near ideal. Near ideal means what? The losses are less. Okay? Losses are less. Hysteresis is there, but it will be minimum. And of course, very durable, robust. Small ranges are also available. Plus or minus 2 mm to plus or minus 10 to 15 mm, plus or minus 20 mm I have seen. Plus or minus 50 mm I heard, but I have not seen. But not very big ranges are not available, but small ranges are available. Mostly in industry, you want to know only the variation in the dimension. So that plus or minus 10 mm, plus or minus 20 mm, it's good enough to meet most of the engineering applications. So it finds a lot of application in the industries.